Okay, so here we are, just looking at a triangle. Now it turns out if this equilateral triangle is going to have area of 1,
Yeah.
do you want to know what the sides are?
Well.
You ready for this?
Sure.
Yeah.
Each side has length 2 divided by the 4th root of 3.
Whoa.
Whoa. But that, that's okay. That's a number that's a little bit bigger than 1. So if we use your idea and draw circles, where do you want to put the circles?
We can put just put the circles on the edges.
On the edges. Okay, so at every point on the edge we draw a circle of radius 1. That?
Yeah.
Okay, that's an interesting idea. And then when we add together all these circles, we'll have it. Do you have any thoughts on this?
Not really.
Well, there'll be some overlaps.
Ooh, there will be some overlaps, but every single point in your idea, every single point's going to have a circle.
Yeah.
So maybe they don't overlap. What does it start looking like? This looks. What can you tell me about this out here, maybe? About your brother?
Well, this kind of looks like a Venn diagram.
Oh, it does kind of look like a very complicated Venn diagram. What about the shape of the outside of this?
Well, it's eventually going. I think it's eventually going to turn flat.
Ooh, yeah. Can you see why? Can you see any geometric reason why we might see a straight line out here?
Well, you're putting a circle on every single point, so there's going to be infinite circles.
There are going to be infinite circles, but infinite circles don't necessarily make a straight line.
Yeah, but what makes the straight line, I think, is the top point of each circle.
What's special about that top point?
Because all the top points are going to be right next to each other, so that's going to make a straight line.
That's true. They all are going to be right next to each other, but there's something else that's special about those top points. Remember the problem we're trying to solve?
Yeah, those are the ones that we want. That are one away from our triangle.
This top line up here is just almost like we just took this line here and just moved it up how far?
Well, it's a 1.
1. Yeah. And then we curve around the top.
Yeah.
Then we move this line up 1 and come down. Then we curve around,
Wow.
move that down, go across, and then curve around like that. That's an interesting looking shape, isn't it?
Yeah.
So, and we don't know how to, in this example, it'd be two-dimensional example instead of the 3-dimensional example. And now we're just going around, so we're trying to find the perimeter. Now, we don't know, in this case, necessarily what this perimeter is, but we do know.
It's curved.
We do know these 3 lengths.
We do know those 3 lengths because all of those are 2 over the 4th root of 3.
Yeah.
This is a 60-degree angle. This is a 90-degree angle. That's a 90-degree angle.
And that makes this is 60 because of our opposite angle rule.
What's 60?
This.
Does it look
Oh
like
wait,
that's
no.
60?
No, the lines don't extend it right.
Right, the lines don't extend right. How can we figure out what this angle is?
Well,
Well,
we could draw a circle around it because
Okay.
angles in a circle add up to 360.
Angles in a circle add up to 360. What's 90 plus 90?
it's 108.
180. 180 plus 60 is what?
It's
100.
240.
And how much more? Can you tell
I
me?
think it's 120 degrees.
Very good. 120. This is 120. That means this is 120. That means this is 120. So all 3 of these little arcs together have an angle of
120. It's 360.
360, which is what shape? If we put them together,
Circle.
it's a circle.
These
So-
are this is each a third of a circle.
That's pretty interesting, right?
Yeah.
Hey, so that was cool. All right, so we figured it out in 2 dimensions, even if some of the calculating the geometry, like 2 over the 4th root of 3, would have been hard. You ready to go to 3 dimensions?
Yeah.
All right, here we go.